All right, welcome everyone to week 5, day 2. Let's go over the quiz real fast. You guys did not do well on it. So, this is the algebra that I was talking about last time. And you kind of need to know this if you're a computer science major, right? If you've got a 3D array and you want to access plane 5, row 2, column 7, where is that in RAM? Like if this whole thing was treated as just a 1D array, where is that in RAM? Because that equation that we went over last time is something you're going to see probably going to see in your career repeatedly. So it's worth going over one more time at least. So maybe more than one time. Maybe we'll do a whole programming assignment on it. We'll see. So if there's 50 rows and 20 columns, then that means that there are 1,000 elements per plane, right? So every time you go down one plane, you're moving 1,000 elements to the right in memory. Do you guys understand what I mean when I say that? Let me pull up OneNote. If it's row 10, column 3, row 9 is the last full row. Yeah, it goes from 0 to 9. If there's 10 rows, it goes from 0 to 9. Okay. So let's talk about this. So if you're in a, well, yeah, I'll just use the values from the quiz, I guess. 10 planes, 50 rows, 20 columns. Planes, 50 rows, 20 columns. Okay. So that means for every plane, there's 50 rows and 20 columns. So every time you go, like if you're at 0, 0, 0, plane 0, row 0, column 0, if you were to go to the next plane and be at plane 1, row 0, column 0, you've just passed over 1,000 elements, right? There's 50 rows, 20 columns. So every time you go down one row, you're moving 20 to the right, plus 20. And every time you move 1 to the right in a column, well, that's just plus 1. And then every time you move down a plane from plane 0 to plane 1, well, that is moving forward 1,000. Because there are 50 rows and 20 columns, there's 1,000 elements per plane. So if we go from 0, 0, 0 to 1, 0, 0, we are now at index 1,000. Okay? And so whatever our base is, remember, we'll have a pointer to 0, 0, 0 usually. Then our offset is going to be 1,000. And technically, in assembly, it's going to be 1,000 times whatever the size of our data type is. Right? So if it's integers, it'll be 4,000 bytes to the right. If we're doing characters, it's 1,000 bytes because characters are 1 byte. So in assembly, the assembly is kind of coded to match the base plus offset syntax. You know, if you wanted to load an integer, from 100, it would be LDR, not LDRB, LDR. Right? There's also half words, which I don't really use that often. So if I want to load into register, register 10, and let's say the base, let's say this pointer here is in register 9, and the offset, which is 4,000, is in register 8, then I would load like this. So that's the base. That's the offset, though technically it does not matter because all it does is just add the numbers together. It's like we saw last time. If you want to really explode people's brains, you can write this in C, and that will compile C++. That'll compile and run just fine because all it's doing is just adding the two things together, and that's true for C and in C++. Ugly, beautiful. Just make sure that half of your half of your array accesses are like array I, and then the other half are like I square bracket array, and no one will ever be able to fire you. It's amazing. So yeah, in assembly it's the same way. It just adds together the R plus 4,000, you know, whatever the base is plus the offset. It'll just add them together, but it doesn't do that type conversion for you. In C or C++, if you have a let's not use ints; those are too boring. Let's say we have a double array, a double array of size 1,000. If you try accessing element 50 out of it, if you say cout, switching to C++ now, array element 50, how many bytes to the right of this is the base, right? That's a pointer. How many bytes to the right of the base is array square bracket 50? You guys know? How many bytes to the right? What's the offset? How far is it from the base? Zero? No. Array square bracket 50 is obviously we're accessing a memory element not at R and R0 are the same memory address, right? If you were to cout R and the address of R square bracket 0 are the same thing. This is the same thing, right? If you were to just cout R, it would print the memory address. Or if you cout the address of memory, if you cout the memory of element 0, then you will get the same thing. R is just a pointer, really. Pointers are just integers. Nothing scary about them. Okay. Anyone? How many bytes to the right is this person here? R square bracket 50. We've got 200, we've got 0, we've got Connor McLaughlin counting to 10, I don't know what that means, and DeBello has 3,200, Guerrero has 400, Manmeet Singh has 50 times 4, Dolio has 8 times 50, Alan has 400, Bacalar also has 400, yeah. So a double is 8 bytes. Okay. That's why it's called a double. A single is a float, and a float is 4 bytes. Okay. So this memory address here, if you were to cout the memory address of array square bracket 50 and subtract from it the memory address of R, then this would print out 400. Okay. Might print it out in hexadecimal, which is pretty common for those sorts of things, but it'll print out 400. Okay. We are 400 bytes to the right. C and C++ do this conversion for you. Anytime you use square bracket, it'll multiply the array index by the size for you. This is not done in assembly. This is not done in assembly. In assembly, if you try accessing element 50, it will segfault. It will segfault because if you put 50 here for R8, it'll segfault. I think. Yeah. It'll segfault because 50 is not divisible by 4. Anytime you do an LDR, you must read from a memory access divisible by 4. You need to multiply the offset, you know, like if we're accessing element 1000 here, you need to multiply that by, in this case, we're doing integers, so it would be by 4. So you'd put 4000 into R8, and so whatever pointer you have plus 4000, that's the place where you're going to be loading from into R10. A 32-bit system will grab 4 8-byte segments at a time, assuming it's a double. A 32-bit system, when you do LDR, it loads a word by default. So, you know, one of Dave Chappelle's favorite words is word, right? So you've got byte, which is 8 bits. You've got nibble, which is 4 bits. You've got a bit, I guess, top here. A bit is 1 bit. We changed the value of $1 from $1 to $0. Bit, yeah, so you go bit, nibble, byte, and then you have what's called a half word. Half word is also known as a short, and that is 16 bits. And then you got a word, which is 32 bits. And that's all you got in ARM32. If you move to 64-bit platforms, there is double words. When we learn the VFP/Neon stuff, there's a coprocessor on our ARM32 chips that actually do. It's actually bigger than 64-bit processing, and we'll learn about that. But it has a double word and a quad word as well register. So there are double words. A double word, which is 64 bits, and there is a quad word, which is 128 bits. Okay. And so there are quad registers called Q0. The double registers are called D0. Regular registers are R. The R registers are words. The double registers are doubles, and the quad registers are quads. However, these two registers are actually the same register, just named differently. So, quad register 0 is the same thing as double register 0 and double register 1 put together, but don't worry about that for now. That's a later lecture. And if you want to do floating point stuff, that uses the VFP, the vector float processor, coprocessor that's built onto our Raspberry Pi CPUs. And Neon, which allows you to do 4 operations at the same time. 4 operations at the same time. In Neon, it's the equivalent of SSE and SSX and what's the other one? AVX and all that kind of stuff that Intel has in ARM. In the ARM world, it's called Neon. I think I'm just still trying to fully understand LDR. Yeah, so LDR loads a word. Okay, it loads a word. So if you were to, if you wanted to, let's pick a different number. Let's say you wanted to load, given this array here. Let's say you wanted to give an assembly command.
That mod that you got with the mud crab in Skyrim. It's actually to get a mud crab as a pet.
You can have a mud crab as a pet.
Yeah, that mud crab is following me.
Nice. Okay, so given this 3D array, we got 10 planes, we got 50 rows, 20 columns. What offset, like what value would need to be in R8 in order to load from 2, 3, 4? What do you guys think? So remember, every plane you move down is 1,000 to the right. Every row you move down is 20 to the right, and every column you move is 1 to the right. Okay, because a 3D array is really just a 1D array, and we do something called row major ordering. So rows are bigger steps than columns. 2, 3, 4. So 2 times 1,000 is 2,000. 3 times 20, 60, 2,060, and then 4 to the right past that, 2,064. So we would need to put 2,064 into R8, and then the assembly command to load that person over here somewhere, that integer, it would be, let's see, our pointer is in R9. Okay. So in assembly, we would have to load into register 8. 2064 was it? 3 times 20. 2064. Yeah. 64. You noticed I didn't use move. The reason for that is that move doesn't work with all numbers. LDR is actually kind of a pseudo command, and it'll actually generate multiple assembly instructions if need be. So you can load bigger numbers into here, and then so this is not actually loading from memory. It's actually putting this number into R8, and then if we wanted to load into register 10 from memory, it's register 9 as the base and register 8 as the offset. And so these two commands together, register 9 is already set to the start of the array. That would load element 2, 3, 4 from this big 3D array. Okay. You're not going to hard code it like this, though. If you need to figure it out, you do multiplies and adds. Okay. Do you guys need to... Do you want to do another example? In leg 8, it's using 8 bytes. Leg 8's not real. Leg 8's not a thing. It's just something invented by Zybooks for pedagogical purposes. Which is actually why I have not used the Zybooks until now. Because I don't know why they would invent their own assembly language. Just use the one that exists, right? Just teach people the actual assembly. Like, it's not hard, honestly. Okay, so that's the rule. So if you want to figure out how far advancing one plane to the right is, you multiply rows times columns. If you want to figure out how far advancing down one row is, you look at just the number of columns. And so again, the there we go. We have a koala drinking a coconut. Okay. So the algebraic formula again is this. So the number of the index is equal to your plane times rows times columns plus row times columns plus column. I will make these all caps actually so you can tell that's the size. All caps is the size of the array. So whatever plane you're on times the size of a plane plus what row you're on times the size of a row plus the column you're on. Okay. Every row has column elements in it. Every plane has row times column elements in it. Right? And if you're going to do this in assembly, once you have the index, then the offset once you know what index you're at, like we're at element 2064, then the actual byte offset, you're going to use is index times the size of whatever type you're using. So for doubles, that's 8 bytes. For ints, it's 4 bytes. For chars, it's 1 byte. Okay. The nan percentage off mudcrab, yeah. They did a 0 divided by 0 in the Creators Club store for Skyrim, and so it said this armored mudcrab pet is nan % off. Oh great, more acronyms. What acronym did I go over? How many bits are in a bit again? If you want to do compression, then you just set the number of bits in a bit to 1/2. Yeah. Then it'll compress all your stuff for you. Okay. Any questions about this? I'll put another one of these on the quiz today, and we'll just keep doing that until you guys get it. All right. So, 61% of you guys got that one wrong. We'll do it again until you guys get it, because, like I said, in my career in computer science, that equation of mapping between 3D and 1D came up a lot. And partly it's because I did high performance computing, but it also just came up in my classes occasionally. And so, but yeah, like in high performance computing, like you usually just pass 1D arrays around, and then you do a mapping to map between 1D and 3D. All right, so match the GDB command with what it does. This prints all of the registers. By the way, GDB is going to be really useful for your homework assignment. So a lot of you guys are just probably staring at the assembly code. How many people have actually loaded the locksmith 2, let's say? Hopefully you guys could do locksmith 1. I kind of spoiled that one for you guys. But for locksmith 2, how many of you guys just opened up the source code and just kind of stared at it blankly for a while? And that's your entire, contribution to the homework. What I would highly recommend doing is opening it in the debugger and stepping through it in the debugger. Okay. So IR will print the value of all the registers, and like I said, you probably want to look into how to do TUI mode. GDB TUI mode is a text user interface, and the command to launch it is kind of weird. I don't remember it off the top of my head. TUI overview. Let's see. GDB-TUI. Okay. Let's just show you a screenshot of what it looks like. Like that. All right, so you can have your registers down here. This is x86, obviously. So you can be stepping through your program. And this is your C program, this is your assembly, and then this is your, you can actually view your registers. And you can sit there and step into or step over different lines of assembly. Last time, I kind of referred to that, but I'll go over that again today, because I didn't really explain it well enough, what step into and step over means. So I'll talk about that in a little bit. So print all registers is IR info registers. Runs the program until it hits a breakpoint, or quits, or crashes. Step or next. So we'll talk a little bit about that today. But that will go to the next line of assembly. Okay. And I'll show you guys the difference between step and next in a second. You can also give it a number, so you can say like next 5, and then it will go 5 commands down if you want to kind of skip ahead a little bit. Prints the value of a variable, and B sets a breakpoint. Okay. So those are kind of the most important commands in GDB. All right, so let's go ahead and minimize OneNote. You've looked at 1 and 2? Yeah. I finally got 1 working, stared at 2 for a long time. I played around with it a bit, still commenting what each line does so I understand it. I'm stuck at negative numbers. I haven't done that yet. Well, I poked around with all the comparison and branch statements. What mode do you recommend? I didn't quite catch it. TUI mode, T-U-I, TUI, text user interface. Okay. So let's show you guys cd asm fizzbuzz.reference. So let's do gd then makefile. So I need debugging information turned on. Debugging information is turned on using -G. And there's actually different options for -G that will provide even more information, but in general, -G is all I've ever really needed. a.out, main.f is okay, all right. Okay, optimizer's turned off, obviously. The optimizer will a lot of times delete assembly code. Ooh, what is going on here? What happened here? I broke something. Fizzbuzz.s. It's broken. What happened? don't know what's going on. Let's not worry about that one then. Asym. What's another good one? Oh, it's because I'm not on ARM32. That was the x86 server. Okay, that makes sense. Don't worry, we'll fix this in post. Okay, now I'm actually on the Raspberry Pi, and it will make a lot more sense. Okay, all right. Chmod, everybody minus execute star, make clean, and make, and there we go. Okay. Yeah, the assembler's like, what is this ARM32 stuff you're trying to push on me here? Okay. All right. GDB-2e a.out. Oh, let's see. Did I put -g in? I did not. So make sure you got -g in everywhere you need it. Okay. So, we start off in this is 2e mode, text user interface. It's different from a GUI, right? And so we can, let's see, quit actually. Name of the function is just fizzbuzz. Okay. Okay. So if I type break main, then when I hit run, do you see how there's a breakpoint here now? Right. So I set a breakpoint. Now when I hit run, it will run. When I hit run, it will. When I hit run, it'll run, and it will stop on the first line of main. Okay. And the reason why I do that is because main is not the entry point actually to your program. There's start, which runs before main, and we don't need to see any of that stuff. So, you thought the cow looked odd? Yeah, that was right. That should have been the dead giveaway right there. It's the problem when you have multiple servers. That's Calth Vader, of course, right there. Join me in learning C++, and your training will soon be complete. Okay. For some of you guys, I gave you a special login message. Whenever I log in as you, if you guys haven't fixed the your .cshrc file, I add a secret thing. McVicker got an extra good one. I have toned it down since then, but you get a nice little fortune message in rainbow colors. Okay. So break on main, run, and now we're on the first line of main. Now, if I type next, it goes to the next line. And you can see that it is printed to the screen, calling your assembly fizzbuzz program. And then on this line of code, it's going to call fizzbuzz. Okay. Now watch what happens if I type next. It skipped over it. You see that? It skipped over the call to the assembly function. That's what next does. Next steps over a function call. So next and step are the same as long as you're doing regular stuff like x equals 5, x equals 10, that kind of stuff. If you know, but when you do next on a function call, it goes over it. So the function call will go, it'll do its thing, and then when it comes back, that's where next stops. So next will stop there. So if we're here, set a breakpoint on line 33, run, and then when I say next, it will go to line 34, and the c-out from fizzbuzz is going to screw up the screen. So you can always hit Ctrl-L to refresh the screen, or you can type refresh if you want. I think that does it, but Ctrl-L is the general Unix shortcut to refresh the screen. So if I ever wall and broadcast a message, you guys just hit Ctrl-L and it'll redraw the screen. Okay, so because I hit next, you guys see that? It it just stepped over FizzBuzz and it went to the next line. And this is really useful when you're in your assembly code and you know, you do like a print or something like that. You don't want to step into it most of the time. Like if you do a branch with link to printf, just step over it, do a next, right? Because just let printf do its thing. You don't need to see the assembly code for printf, trust me. So what we can do instead though, start from the beginning, yes. And so breakpoint 1, run line 33. Okay, now step instead will go into the function. So step steps into the function, next steps over it. Do you guys understand the difference? So if you do step, it will then take you inside the function. You can trace the flow of execution inside the function. Whereas with next, it steps over it. And that's useful if you have a lot of function calls, like just standard library stuff. Usually most standard library stuff, I step over it. I don't need to debug the standard library. You know what I mean? Like I'm usually pretty confident. I have very, very rarely found what I would consider to be a bug in the standard library. It's almost always your fault though when something breaks. It's very very rare for the standard library to have the bug in it when your code's not working right. So does it work the same way with branches? No, BL. Yeah, branch with link is a function call. Okay, so here we are in my assembly code, and so I can just hit return. By the way, if you don't want to type step every time, watch, just hitting return. And I can show the registers. There we go. And like I said, you can set up the registers. I don't remember all the different TUI commands and things like that because I don't use it enough. But you can actually have your registers displayed on the screen as you step through the code. Okay, and so step, and then just keep hitting return. And then here's the print number function. So I don't really want to do that. So I'm going to type next, and then every time you hit return, I think it repeats the last command, right? Yeah. Okay. Control-L to refresh. Okay. And again, if you want to check the values of the registers, you can print them out. And next. Right, and so what I recommend doing is attaching the GDB to the process while you're doing your lock picking assignment. Okay, so rather than just like looking at this sea of assembly and being like, I don't know, dude, run through the code, see where it's asking for the password, and see what it does with the password when it comes back. Okay, so that's my advice to you. Right. So GDB is used a lot when you're reverse engineering stuff because you can sit there and look at the different values and set breakpoints and run them and things like that. Is there a way to have the registers constantly being updated to the screen as you step through? Yeah, there is. I don't remember the command off the top of my head. Like I said, I don't use it enough to. GDB TUI show registers. I can Google it too. You know. Source. Yeah. So there's a register window. TUI key bindings. Control-L refreshes the screen. Layout next. Layout split. Focus next. So let's try this. Let's try Ctrl-X 2. Let's try that. There we go. Ctrl-X 3 maybe. No. Breakpoint on line 33, run, step into it, and there's the assembly and there's the compiled code. Let's see, layout, next. There we go. All right, there you go. That's probably what you're looking for. So I hit Control-X2 to go into two windowed mode. And then I type layout next to switch it to assembly code here, and the register is up here. And so as I step through it, and again, I can just keep hitting return, and it'll keep stepping. Once I get to print number, though, I want to step over it, so I hit next instead. Control-L to refresh the screen, and you can see the values changing as I hit return. Okay. So, yeah, so Control-X2 opens, Control-X1 is one windowed mode, Control-X followed by 2 is two window mode, and then you can do layout next to change the, that's the compiled object code. All right, so yeah, I'll post this link into Discord for you guys. So yeah, 2E mode's pretty cool. I recommend it. Yeah, in Locksmith too, the reason why you're not seeing it on the screen is because I'm looking at the original source code. So I did things to disguise what the secret numbers were and things like that. I use shifts to shift the values around so you can't find what the actual answer is. It's only about 2, 5, 6, 7, 8, 9, 10. It's only about 15 lines of C++, maybe. A couple functions. Yeah. Yeah, I might have broken it when I updated the server. So I'll get back to you guys on that. Okay. So, thank you, Walker. Yeah, there's an auxiliary function that called Cryptomatic 9000 that I call to decipher the strings. Let me just see if I can find that. Yeah. It's a very highly secure BSD games. Sudo apt install BSD games. So normally in this class, while this is installing, I'll tell you guys, normally in this class you'd be handed a Raspberry Pi or two and you would learn to administer your own machines. Yeah. I don't know if that's going to happen this semester. Let's see, do we have ROT 13 installed? Hello, my name is Bill. Yeah, so it is a highly secure encryption system that adds 13 to a letter. And if you add 13 to a letter again, it decrypts it because it wraps around its modulus. Right? It only works in English because we have 26 letters, right? So if any of you guys want to know what your hacker name is, Dolio is Quibi, Hazelton is Mr. Yigiba, Tran is Gina, Walk Up is Jinsixth, Nate Beal, of course, is Orny. Anyway, so Rot 13 is welcome to the game. So what happens is the locksmith code calls Rot 13. So the strings that I have given to you guys are Rot 13 encrypted. So you can't just Google them and find out where the answers are. Okay. Or just meet somewhere for half an hour and distribute. I might. Maybe after the midterm. For now, like I said, we're gonna go heavy on assembly programming this year. Normally, I kind of jump back and forth between architecture, assembly, and physical computing. This semester, it's been like 80% assembly and a little smattering of architecture so far. I'm just trying to get you guys all up to speed on assembly programming. Okay, so Cryptomatic 9000. Don't you know who I am? Permission denied. What is this? Windows denying me permission when I'm running as super user? Okay, so are you guys familiar with the ln command in Unix? A little bit of Unix trivia here. Those nodes. Natural log, right? No op, a little. Okay, so in Windows, are you guys familiar with the concept of a shortcut? Like you can right click on a file and create a shortcut to it somewhere else. Have you guys ever used that before? So that's what ln-s is. It creates a symbolic link to a file. So it's basically a shortcut. If you delete the original file, the shortcut stops working. If you don't use the -s, it actually creates a copy of the file, but they're actually pointed at the same place on disk. So you can actually have two copies of a file that actually use the same hard drive space. And so if you edit it over here, or if you edit it over here, it'll actually edit the same file. So ln works just like copy, except it doesn't make a copy. It makes a link to it. And so every file in Unix can actually have multiple ways into it, multiple links to it. It's called a hard link. But ln-s is the symbolic link, which works like a shortcut. So what I'm going to do is I'm going to make, let's see, echo path. Games is in the, okay. So I'm going to make a shortcut, sudo is needed, ln-s. I'm going to copy user games rot 13 to user games Cryptomatic 9000. Are any of you guys getting error messages that Cryptomatic 9000 can't be found? Are you guys seeing that? Okay. And sudo chmod changes permissions. Everybody may read and everybody may execute -user -games /Cryptomatic 9000. And so now if you run Cryptomatic 9000, it will run rot 13. Okay. If you do ls by default, if you just ls the file user games Cryptomatic 9000, it just prints it, but it'll show you that that little thing there indicates it's a shortcut or it's a symbolic link. If you do ls-l, -l with ls means long information, it will actually show you this program here, Cryptomatic 9000, is a shortcut to, it's a symbolic link to the rot13 program. Okay, so when you run Cryptomatic 9000, it runs rot13. You thought chmod was Hamad's evil twin. Does it work with includes and stuff, like through a symbolically linked file? It should, yeah, like probably locate iostream. Yeah, probably some of these are going to be aliases for each other. Locate vim. Gosh. Let's not do that. Which vim? Vim is the alias to nvim. Okay, fine. Which nvim? User bin nvim. No, let's unalias vim. Which vim? User bin vim. Okay. So you can see that vim is actually not a program on here. It's actually a shortcut. And so it's a shortcut to etc alternatives vim. So etc is where you put like configuration stuff on a Linux box. And there's a really cool program called alternatives that allows you to have installed multiple versions of vim. And just by editing whatever this thing is, you can change which vim is installed without having to uninstall and reinstall vim over and over again. There's a program called update alternatives for vim. What's it called? Update alternatives list vim maybe. What is it? Config vim. I don't remember the syntax on it. Get selections maybe. So you can have multiple versions of vim installed, and then you can use update alternatives to choose which one is run when you actually type vim. Let's get selections. Do I need sudo on this? That's why it wasn't working. Okay. So vim is set to vim nox. Okay. There we go. And so these are the different versions of vim I have installed on the server. And in vim, vim basic, and vim nox. And so I can choose to leave it as vim nox as the default vim, or I can choose to set it to new vim. And since new vim seems to be working better than the old one, which broke for some reason, now if I just type vim locksmith.s, you see it launches in vim. You see there's that cool bar at the bottom there. Q.s. Okay, so by using update alternatives, you can choose which one of the vims you have on your server actually run when you run vim. It's like a system-wide alias kind of, and that all takes place via the fact that this is actually a symlink, and this. So it links to etc alternatives vim, and etc alternatives vim is actually a symlink to nvim. So vim is a shortcut to etc alternatives vim, and that's a shortcut to the actual vim. So it's like multiple layers of indirection. But by doing that, you can have vim nox and vim basic and nvim installed on the system as I do, and you can just switch which one's the default by running update alternatives, which changes this hyperlink here. And you can do that for G++ or GCC. CC would be the compiler, and so you can choose: do you want to use GCC or do you want to use Clang? And you can pick which one is your default compiler, right? So, yep, you can have different versions of GCC installed, you know, and yeah, update alternatives is kind of cool, and you'll learn about that stuff whenever you administer your own machine. Why have you disabled Steam locomotive in favor of another ls command? Yeah, so I could install SL. I don't have it installed. Let's do that. Sudo apt install SL, and there we go. It's 11K of space. It's gonna eat up all my hard drive space, I tell you. So SL is Steam Locomotive. It is a command designed to teach people not to type ls backwards. But I have an alias set up, so if I type ls backwards, it does ls, you know, as a quality of life thing. But if I were to, by the way, if you run a command with a backslash in front of it, it doesn't use the alias. So if you want to run the original SL, update my path, then you can see SL, and Control-C doesn't work. You can't Control-C out of it. You just have to wait. You just have to wait for it to finish the animation. And if you know the secret kill command, then you can still kill it. Secret kill command is Control \\, by the way. That is kill with prejudice. Control-C is interrupt, which normally will kill a program, but like, let's say you're in Vim locksmith2.s. Let's say you're in locksmith2.s and you hit Control-C. It actually doesn't quit Vim. Control-C is trapped. There's an interrupt and it traps it, and it doesn't quit. It'll print a little message down here, like type this to quit. But if I were to do that with Control \\, it should kill it. Oh, it's not killing it. Interesting. Neat. Hold on. Well, in any event, when you run that, if you hit Control \\, it will kill the program with prejudice. Okay. And my screen's broken now. See how there's no cursor? So let me go back into Vim and quit, and quit, and the cursor's back now. Okay. Your Vim is beeping at you now? Yeah, I don't know why NVim does that. NVim has this issue where it'll just start beeping, even if you have all the options to turn beeps off. I don't know what the hell's going on with it. I used Control \\, your cursor's invisible. Yeah, it'll do that. That's why you don't want to use it most of the times. If you hit Control-C, a well-behaved program will trap the interrupt and handle it. So let me switch back to the regular server real fast. Kill with emphasis. So if we go into here, cd edgelord.reference. So here's a program that will generate a random map and do edges between the different countries and things like that. And has mouse support, so Madrid can conquer Hong Kong, Madrid can conquer Geneva, so on and so forth. If you Control-C out of it, then it successfully resets the screen and successfully turns the cursor back on, which it was off. And trust me, if I run this with, if I run this, Las Vegas is going to conquer the world. If I do Control \\, then the cursor's invisible, right? So a well-behaved program will trap the interrupt, the Control-C, and will return control with everything set back the way it was before. So let me show you how to do that real fast. Main.cc. So, because this is actually relevant to C-Sci 45. So this is a standard library function. Is that how you want us to print the names for edgelord? That's how you're supposed to do it, yeah. You're supposed to put a tag in the center of the province. By the way, I don't think there's class tomorrow, so those of you in IS50B have another week to do stuff, I guess. I don't know. I'll have to come up with something for you to do. Might have you make a shader or something. I don't know. So let's learn some new things. You guys want to learn some new things, or do you want to just not learn new things? What do you guys feel like? Learn? Okay. So @exit. This is a... Do you want to play games instead? Okay, sure.
There's an escape man at a room, and I did the first question, which is usually the hardest. But I noticed that some of the words were French, and guess what? It was actually France.
It was French?
Yeah.
What was this? In Skyrim?
It was like... no, it was like an escape room, digital escape room.
Digital escape room? And you knew that it was in France because the words were in French?
Yeah.
Nice, girl. Well done. Now, then your next assignment is you're going to have to be able to detect the difference between Chinese, Japanese, and Korean. Okay? Okay, good girl. Only by their different use of characters. She runs out. So this is a standard library function. And, you know, this is something that I kind of harp on a lot, but, like, one of the biggest differences between an inexperienced programmer and an experienced programmer is just knowing what exists already. And the inexperienced programmer will try to reinvent the wheel left and right. Like okay, I need a program, and I need to do something when the program quits, and so they'll sit there and try to engineer like something that'll monitor another process, and when that process dies, it does something, it refreshes the screen or something. Yeah, you don't need to do that in most cases because there's a function called @exit. This won't get called if they control / out of it, but control / is the kind of thing that only power users know about anyway, and they're willing to accept the risks. So @exit registers a function. This is something called a function pointer. Okay, so it registers a function with @exit that it's a function that returns nothing and takes nothing. And so basically what you're doing is you're creating a callback. And so the notion of a callback is really important in computer science. And most of your programs to date have not involved callbacks. Most of your code you just run main and it runs and it does stuff. But a callback means you have a function and you say when something happens, call this function. And this is a different flow of control from like main, where like main starts at the top and goes to the bottom, and maybe it's got some function calls and maybe it's got some loops and things like that. With a callback, what you do is you register a callback with the system, and then when an interrupt happens, or something happens, then it calls that function. And so in this case, when the program terminates, it'll call this function. And so what I have in my code here is I have a function called bailout. I wrote this. This is not part of the standard library. But I'm registering bailout with @exit. And so bailout is where? It might be in the header file, actually. Grep bailout star. It is in the header file. Okay. So bailout is a void function that takes no parameters, right? Like we just saw that. So I register with it a function, and when the program quits, no matter how it quits, it will call this function here. And what this does is it turns, it puts the terminal back into a state where the cursor is turned on, and everything is kind of working the way that it clears the screen. Yeah, and so basically this is going to, I could probably even like do this. So when I hit ctrl-c, it actually calls system clear, which will clear the screen and move the cursor back up to the top and stuff like that, which looks a little bit nicer. What I had before was the cursor would be down here somewhere. And so by doing that, it actually puts clears the screen, puts the thing up top, stuff like that. And it's complaining at me that I'm ignoring the return value from this, so but if I catch the return value and compile it again, then it's going to complain clean make it's going to okay. It should normally complain that I don't have I turned off no unused variable. Yeah, okay, that's fine. Okay, so it's like a destructor in C++, yes, but for the whole program. Exactly, that's a really good way of thinking about it. And this should be relied upon quick read. So yeah, atexit is like a destructor for the program, but this is C. Right, so this is C, not C++, so they don't have destructors. And so this is a way that you can make sure that anything that needs to be cleaned up gets cleaned up when your program terminates. And so that'll apply even if you call exit, right? When you call exit, exit's not the end of the program, as it turns out. Main is not the beginning of the program, and exit is not the end of the program. Neither is the bottom of main. Like when you finish main, that's not the end of the program either. What happens when main terminates? That's not the end of the program. What happens is then it moves into the exit routine. So start calls main, and then when main finishes, it calls the exit routine, which does various cleanup things of the standard library stuff if needed, and then it will call all of the functions that you registered with @exit. And I think it calls them in reverse order. So if you @exit A, @exit B, @exit C, 3 functions named A, B, C, then I believe they get called C, B, then A. And they can be used as like a destructor for your entire program. So, can it have parameters? No, it has to be a void function that takes no parameters. It's just a plain void function that gets called when your code terminates. So the argument of @exit must be a void function with no parameters. That is correct. Yeah. So you just pass in the name of the function. Notice that I'm not calling bailout. You guys see this? I'm not calling it. I'm actually passing the name of the function as a parameter. I'm passing a function as a parameter to another function. Kind of like when we sort. When you call sort on a vector, you can pass in a function that'll be used to sort the function. And then here's another callback. Okay, so this is another callback right here. So signal is a really important thing that you guys all need to know. So signal, also part of the C standard library. Signal allows you to handle interrupts of various kinds. So a signal handler function is a function that returns nothing but takes an integer as a parameter. So this is a little bit different from @exit, right? @exit takes a function that returns nothing and takes nothing. Signal takes a function that returns nothing but takes an integer, and the integer that it takes in is what signal was passed to it. So you can have the same signal handler for multiple signals. Okay, and then this is the actual function call you make. So you make a function called a signal, you say which signal you want it to handle, and then a callback, the callback function. Okay, so so these are all the different signals in the Raspberry Pi. So there is SIGINT, that is interrupt, that's ctrl-c. There is SIGKILL, which is 9, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Kill-9 is kill. Basically. it's SIGKILL. And that is killing something with prejudice. There is no ability for a process to ignore a SIGKILL signal. And so I do this sometimes, like if I'm running htop and I see that Benninghoven is eating up all of my CPU power. In the past, I've run quotas for students, but in general, it's kind of like, well, all right, let's say a student has a runaway program and they run out of quota. Are they just not going to be able to program for the rest of the semester? Like, is that the solution? Just like, sorry, you used up all 10 hours of CPU time. You're done for the semester. You know, I don't know. I don't. Maybe I should put quotas back on, but it seems to work decently well so far. So let's say I wanted to log Biddinghoven out. Okay. So every process in Unix has a number. Like basically everything in Unix is a number. Every file is an, you know, every socket you have is a number. Every signal has a number. Everything's basically an int because Unix, you know, they're all in registers, and a register is just an int, and so basically everything's an integer. And you know, standard in is file 0, standard out is file 1, standard error is file 2. It's just they're all just integers. Okay, so so you can set up callbacks for various things. Signal is probably the most common callback you'll use. Debello atexit is also used a lot when you need your code to clean up when it terminates. And then you can create your own. Like I created a callback for mouse events in PuTTY so that you can make it so you can click on things. Like you see how like htop here is accepting mouse events? I'm actually clicking on these things, right? And so let's say Biddinghoven, his thing's running out of control. It's 100% CPU for a couple days. Like Garrett's A-star code, yeah. So in CSI 26 a year ago, Garrett's code ran for like 3 days nonstop, trying to find a shortest path solution. And so I eventually I terminated it, right? So his process ID, PID, is a process ID. Every program, every process running on... Oh, somebody's toying with me now. Okay. No? Okay. Yeah. No? Okay. So I'll go back to where we were before. So Biddinghoven's login shell, this is his TCSH shell. That's the only one he has open right now. So he's only logged in once. He's running Vim too, but let me just log him out of the server. So his process ID is 381955. 381955. So I can say sudo kill -9 381955. And so that will send a uncatchable signal of death to his login shell. And then when I run htop, you can see that he has since been logged out. Okay? So, yeah. And so that's kill. Kill actually isn't used to kill things. It actually just sends a signal. So kill is the easiest way of sending a signal to a process, and then the signal function handles it. Okay. So kill will send a signal to a process, or you can send a signal by hitting ctrl-c or ctrl-backslash, ctrl-z. Ctrl-z is the stop, or no, sorry, not stop, background command. Let's say I'm cat. Let's say it's just run cat, right? Cat just will echo back to me whatever I type in. Now let's say I type Control-S. Control-S is sig stop. And so I'm typing things, but you notice how nothing's appearing? So S suspends the program from running. But if I hit Control-Q, then it will resume, and it will process all the things that I typed in there in the meantime. Control-Z will background a process, and then I can type FG to foreground it again, and go right back where I was before. Control-C, of course, quits the program. And so you can have different signal handlers for these different events. If somebody disconnects, like if their PuTTY terminal dies, you'll get a sig hup, sig hang up. In other words, somebody disconnected. And so when Vim gets a sig hiccup, when Vim gets a sig hup signal, then it saves a copy of your file. Have you guys ever seen that before? Like your Vim foo, and I'm like typing things, and I'm typing things, and then let me just kill PuTTY. Oh wait, Biddinghoven's not in this class, is he? Yeah. He's probably very confused what just happened, huh? Huh. Interesting. The perils of computer science. I meant to kill somebody in this class, but I was not on the Raspberry Pi. I was on the other server. So if I were to now edit foo, you'll see, have you guys ever seen this message before in Vim? Do you have screens on the server? I do. I do have screen, and I do have tmux installed as well. Now he only had the README file open, so he didn't lose anything, but it's still kind of funny. If you ever Control-Z, yeah, it'll suspend your program, and so, but you're gonna actually get a different error message if you suspend your program. If you suspend your program and try editing it again, it'll say the swap file is currently in use by somebody else. Okay, and that's different from this. In this, I quit PuTTY while the file was open, and so it saves a copy of it, and so you can choose to delete the saved copy, which I wouldn't recommend. I usually open it first and take a look, and then after I'm like, you can edit it, you can recover the copy. There you go. You can see the recovered copy had the text that I put in there, right? And then if you want to save this one, you can hit W to save, or if I'm like, no, I don't want those changes, I hit D, and then that erases the swap file. Okay. So when Vim gets a SIG-HUP signal, in other words, indicating that somebody closed PuTTY without closing the file in Vim, then it writes a copy to disk. And so this is a very useful thing. And all of them are just handled like this. So you basically make a call. Let's go back into edgelord man.cc. And so this is an example of how you do it. So I say when the SIGINT signal, SIGINT is Control-C. When somebody sends my program the Control-C signal, then call this callback. Okay. Callback to handle Control-C events. Okay. Is swap a Unix standard file type? There are no standard Unix file types. I think SWP probably came from the DOS world, but yeah, it's not a standard type. Yeah, tmux is cool, screen is cool. Can you go over signal again, and what are the parameters? Yeah, so basically signal is the name of the function, and the first parameter you pass to it is which function you want to handle. In this case, SIGINT. SIGINT is Control-C, and I'm saying when a Control-C comes in, call this function. Call interrupt handler. And there's other options for signal as well. There's sig-ignore and sig-default, like that. And so if I want, I could do that, and then that would revert to the default signal for Control-C. So I can make it in just parts of my code. You can't Control-C out. But then in other parts, it would go back to the default handler for Control-C, which kills your program, right? So you can do that. Or, let's put that down there so I don't break anything. Or you can do this, sig-ignore. Actually, let's do this. Which will ignore all Control-C. Does that make sense, Robert? So if you don't want your program to die when somebody hits Control-C, 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 Control-C. Sorry. So these are your three options, you know, and everything defaults to the default. But if you want to change it, and so interrupt handler, grep, interrupt handler. So grep, by the way, if you have a lot of files, grep is your friend. So grep allows you to search through all the files in a directory. So I'm going to search for interrupt handler, enter in all files, and I find it is used here in main.cc, and it is defined in quick read, right? And so the Unix operating system is an IDE, and a lot of people don't really understand that. Like, it's you know, all these tools in Unix, a lot of them are designed for programmers. To develop, right? You don't need Visual Studio. You don't need any Eclipse or any of these things. Like, the Unix operating system itself is like in Visual Studio Code, that'd be like Ctrl-Shift-F to search across files, and in Unix you can just use grep, and grep has a very, like, this is the most basic use for it. You can dive really deep into grep and do amazingly good searches, way better than you can with Ctrl-Shift-F. Control-Shift-F just searches across all the files. grep, you can pass in patterns and all sorts of really cool stuff. So, quick read.h, interrupt handler. So when I hit Control-C, it's just calling exit. Okay, so and that will call @exit. @exit will call bailout, and then that will handle that. Okay. All right. It just doesn't have a GUI. Yeah, it's so. Who needs a GUI? Right. Text is much faster because a GUI involves a mouse, right? And mice are not fast. Text is much faster than mice. It looks like you're a hacker man, with the second you pull up a terminal, it makes you look like this guy here, right? But most experienced programmers either prefer the terminal or they've never used the terminal. those are, as far as I can tell, those are the only two options. Is people that think the terminal's superior to a GUI, or they're people that just never took the time to learn it, and by this point are too afraid to ask. Okay, so the Unix IDE of war games, yeah. So okay, it's a Unix system. I can hack this. Yeah, Jurassic Park. Good. All right. All right, so do you guys kind of understand Signal? So this will actually lead us into our next topic for today. Okay. And that topic is system interrupts. All right, so how do I print something to the screen? In assembly, right? Not by calling printint or printf or cout. How do I print something to the screen in assembly? What do I do? Echo? Is there an echo command? So, puts is a C function. Cout is a C++ object that has an operator double left arrow to print things. How do I actually print something? Like, because you can't print, like, if you're, like, obviously, printing something to the screen is not actually done in C or C++ because then C would just be calling C, and C would be calling C, and there would be no way of actually printing something to the screen, right? So you might have seen me at different times put a number here, like printf3. Have you ever seen me do that before? The reason for that is because there's different chapters of the manual pages, right? Man chapter 1 is Unix commands, right? So if you want to learn about grep, there's manual pages for grep. Different options for grep, there are a lot. And so there is a command called printf, hello. Right, there's a Unix command called printf, and then there is in section 3, section 3 is the C standard library. So section 3 is the C standard library, section 1 is Unix commands. Section 2, though, is our topic for today. Okay, so man to write. So section 2 is how you actually get stuff done. Okay? So this is how you actually can do something in Unix. Windows does its own thing. Section 2 is the Unix interface, the Unix system call interface. In other words, C and C++ have no ability in and of themselves to actually print anything to the screen. In order to print something to the screen, you must go through the operating system. The operating system, what an operating system is an interface between programs and hardware, and it mediates access to that hardware. You cannot just write to the hard drive, right? Because that would be a huge security risk. If you could just write to the hard drive and tell the hard drive, go to sector 50 and change Kearney's password to this, that would be a huge security problem. So what there is there's the hard drive, and then there's the operating system. The operating system has a driver in it that knows how to control the hard drive. And then your program tells the operating system to write to disk some data. And the operating system will check to see if you have permissions. If you try writing to the password file on the server, cat into etc password, you will get a permission denied error. You cannot write into the password file. Now, if I did this with sudo, which I'm not going to do because that could destroy the server, I could do it because I could elevate my permissions to have root permissions, super user permissions. Okay. So if you want to actually write a file to disk, you have to use write at some level. Okay. If you want to read from the keyboard, or if you want to read from a network socket, you have to use the read function. And that is also in section 2, man to read. Okay. So write is really the only way you have of writing to disk, or writing to a network socket, or writing to a pipe. That's it. Writing to the screen. Write. All of them go through write. And if you want to read from the keyboard, if you want to read from a pipe, or if you want to read from a file, or if you want to read from keyboard, file, pipe, network socket, you use read. And that's it. This function is how you actually get data into your program. And this is an operating system call. Okay? And so let's break this down a little bit. Let's talk about read and write today. Because all C does with printf and scanf is they are a wrapper around read and write to make it easier to use. And when you do cin and cout, they're wrappers around read and write to make them easier to use. And it also has some compatibility features with C so that when you do cin and cout, you can also do printf and scanf as well without breaking things. Okay, you guys ready for this? Do you guys want to learn how to actually read and write and how files work and stuff like that? You guys ready for this? Okay. So let's do it in C first. Before we move into assembly, let's do it in C. Okay, and so all of the Unix system calls are in Uni standard library. So this is the Unix standard library. Okay, and you can think of this standard library as being below the C standard library. So you've got your hardware, like your hard drive, and then you've got your kernel, the Linux kernel, and then your program is going to call functions in the Linux kernel. And the interface for that, the API, the application programming interface for that, is here. It's in the Unix standard library. Okay. Temple OS, that's funny. As long as we have time to finish, don't leave me more confused when we started. Sure, we got time. All right, so let's make a program called vim main.cc. I'm just going to do it in C++. Oh, what happened to my macros? Arrgh. No, my macros are gone. I'm gonna have to type this out like a peon. Okay, include Unix standard. I could just do that. And using namespace nothing. Not using namespace anything. Okay. Int main. I'm not using IO stream. I'm not using standard IO, C standard IO. Nope. We're going back to basics here, and we are going to use the Unix standard library interface. Okay. And I will clone this window so I can have the man page open on the right, man, and we're going to start with open. Okay, and so open is open will open a file. So let's say we want to open a file to write to. Okay. Macros are gone. I know, dude. It's probably because I messed with the vim thing. Okay, all right, so. Oh, yeah, this is 2. Okay, all right. I don't know if I need that, actually. Whatever. All right. Okay, so let's open a file. And so I'm going to open a file in the current directory. Dot is the current directory. Dot / current directory. And I'm going to call this file macros are gone.txt. Okay. And then the flags are that could actually be interesting. Probably want that. Must be split. If it is okay. Let's try this. I don't usually create files this way. Okay. G++ main.cc run vim macros are gone.txt. Okay. So you can see that we have successfully opened a file, and the permissions, of course, are not set. Fantastic. So I was afraid of. Okay. Sudo remove macros are gone. Okay, vim main.cc, so I need to specify the permissions on it. We will do use, yeah, okay. irwxu, the user has read, write, and execute. I do not need execute, so user has read, user has write. Okay, so these are actually bit flags, and so I can actually just specify this if you want to blow your mind a little bit. How does that look to you? You guys remember bitwise or, bitwise and, that kind of stuff? So this means that 4 right there means you have read permission, And that 2 means you have write permission, you, the user. And so by making it 6, it bitwise ORs them together. I don't need execute permission. Execute permission to 1. I don't need that. The next digit, this is an octal, by the way, which we'll learn later. The next digit is for group read and write and execute. I'm giving the group no permissions, and I'm giving all of you guys no permissions on this file. Okay. And so set UID bit, don't care. Set group ID bit, don't care. Sticky bit, don't care. Okay. So let's try this again. Compile the code, run it, and then ls-l macros are gone, and you can see, voila, the permissions have been set properly. I have read and write permissions on the file. I don't have execute permissions on the file, so if I try running it, macros are gone, it won't run. Permission denied, command not found, either way. And so this is how you create a file using the standard Unix standard interface. Okay, and so it returns an integer, and you notice I'm not catching it right here. I should be. And so in Unix, all things are basically integers. Okay, so a file is just an integer. A network socket is an integer. A directory, and like everything's an integer. All right, and so we like to pretend that they're not. Like in, you know, we create these, like if we're doing C++, we'd have an IF stream and all this kind of stuff. No, everything's just an integer. And so this is the file descriptor. Okay, so a file descriptor is just an integer. Okay, and what it means is when it opens a file, then you know, let's see this out. Include IOStream. Standard. I really don't need this because I'm going to show you guys how to do reading and writing without it, but let's do this real fast. File descriptor is file descriptor. Yep. And it should be 3. Yeah. Okay. So open will allocate the next file descriptor is usually the next available one, right? And so you can have, I guess in theory, like 2 billion files open. I doubt you could actually do that in practice. But basically, every time you run a program, there are 3 file descriptors open by default. File descriptor 0 is standard input. File descriptor 1 is standard output, and file descriptor 2 is standard error. Okay, and that corresponds to cout, cerr, and cin. All right, cin is a nice interface for file descriptor 0. Cout is a nice interface for file descriptor 1, and cerr is a nice interface for file descriptor 2. But they're all just integers. Everything's an integer. Okay, so let's say we want to write something to that file that we just created. So macros are gone.txt has now been opened. I chose create mode. Create mode means it erases the file and makes a new one. There's also append mode. Append mode will not erase any existing data and will instead add to the end of it. But I am just going to erase it every time, and I want to write something to it. So man to write, and so this is the only way really of writing data into a file or whatever, right? So write takes in a file descriptor. What file would you like to write to? Okay. What file would you like to write to? Well, let's have a character array named string that is equal to ABC. Okay. And I'm going to write to file descriptor FD. R, I'm passing in a pointer. Now you might be saying const void star. What's a void pointer? A void pointer is a pointer that has no type. So it can take any type of pointer. It can take any type of pointer. Okay. And then the third parameter here is the number of bytes to write to the screen. So how many bytes should I write, or not to the screen, but to the file descriptor? How many bytes should I write? What do you guys think? How many bytes are in that string right there? A const auto star. Auto isn't anything. Auto is not a void pointer. There is void pointers in C++, but void pointers in C++ are actually much more limited in a certain respect. They try to do away with void pointers in C++. Let's put it that way. Okay, so we've got 4. We've got 16. You guys think these are integers? Really? Okay. They're chars. Chars are 1 byte. So this string here is actually 4 bytes long. It is A, B, C, and then byte 0. However, we actually don't need to write the null character, I don't think. Let's just try 3 bytes. Let's just see how this goes. And then we need to maybe close the file like that. Close, man to close. You see it just takes in a file descriptor. And all that does is it closes it down, flushes the buffer, tidies everything up nicely. Okay. And I could be checking the, this returns how many bytes were actually written. This returns if it was success. And I'm just going to assume that it's going to succeed. Unexpected initializer before. It's got to be a const char star. Okay, fine. Okay. And so we ran it. Let's see if it worked. Cat macros are gone. Nothing's in it. Interesting. So let's try 4. Nope, nothing's in it. For char per char plus null. Okay. That's man 1. Look, I'm writing to file descriptor 1 now. I'm writing to file descriptor 1, and look what just happened here. Check it out. It's printing things to the screen. Okay. Let's make this, let's add a backslash in here just for the hell of it. I'll write 5 bytes instead. And you can see, there we go. So the write system call is working. Okay. I feel better about all my attempts at file manipulation with C++ now. Lol, thanks, Kearney. I don't know what that means. Did open not return the right value? It's returning 3, which should be the right value. And stir and 5 are working. So why is it not actually appearing in the file? Do I need to flush it? I think so. Does not make any guarantee that it's been committed to disk. Close. The only way to be sure is to call fsync after you're done writing your data. Might have to do that. Right. Transfer most 2 gigs of data. Close should do that though. And fsync. Oh. The hell? Okay. It's writing no bytes into it. Interesting. You know, it's returning file descriptor 3, which is correct. And we should be writing to file descriptor 3 string, 5 bytes. It's not actually printing there. I wonder if my mode is not correct. Okay. I don't use open very often. Let's try this instead, actually. Returning a file pointer, right? Right, because the C standard library uses something called a file pointer, and you can actually pass it a file descriptor and get a file pointer out of it. What is the file now? Okay. This might be kind of terrible, but I'm going to try it anyway. File now. Try this. Segfault, yeah, figures. Does it destroy a file descriptor, freeing a number to be used as a file descriptor for another file? It does, yeah. It does. Run. What is your age? 12. Okay. So let's look at this in assembly, and I'll try to figure out what I was doing wrong in that one. Okay, so here in assembly, we've got we want to convert this code into assembly. So cout is saying, what is your age? 2 digits. And then you type in 2 digits, and then it adds 10 to your age. Okay, so main, we got the push. We put a 1 into R0. So 1 means standard out, 2 means standard error. 0 means standard in, right? So file descriptors are just integers, right? And this is new for today. And you need to know this for locksmith, so pay attention. Okay. What this is doing is it is loading the address of a label, essentially, into register 1. It's loading the address of a label. So if I scroll down to the bottom of the screen, you can see that there's a label called greeting. Okay. And so every label is just a tag on the next line of assembly code, right? And it's just saying that we're giving this a name, right? And so this is a ASCII null terminated ASCII string. It says, what is your age? 2 digits. And that is it's going to load the memory address of the W, basically. So when you do the LDR with an equal sign, this is new, LDR with an equal sign. So it says LDR into register 1 equal sign greeting. That is going to load the memory address of the W. That byte right there. Okay? You guys understand? That's loading the address of the W in the first letter of the string. Down here, we have a data segment. We haven't talked about really a data segment before. You can actually make variables in assembly. And so you can make an array by using .skip, and there's other options for making arrays as well. But basically, if you say .skip 400, you know, something like this, going to make an array, you can say like r.skip 400. And that will make an array of size 400 bytes, just in the data segment. Okay. And then if you want to load the address of R, you just do LDR R1 comma equals R. Like if you wanted to load, you do something like this. You'd be like, load into register, I don't know, load into register 7 the address of R. You guys understand? This is different from what we were doing before, where your C code was passing you a pointer, right? This is how you actually get a pointer in assembly. So that would give you the memory address of this 400 byte array. Okay? Okay. And so and this is going to help you with locksmith as well, right? And so we've got a label here called greeting, and it's a string. It's a null terminated string because it has the Z there. It adds the null terminator for you automatically, which is nice. And so this is going to load the address of the string into register 1. It loads standard out, cout, into register 0. And it loads the length of the string into register 2. And there's kind of a clever way of doing this here. This is actually a very clever trick that basically computes the length of a string. So this is a kind of a cool thing that says take my memory address and subtract the greetings memory address, and so that is the byte difference between me and the previous label, basically. And so rather than you having to sit there and count how many letters, you can do this, and then that will subtract my label from that label memory address and tell you how many bytes it is. Okay, so one way you can do it is you could either just count how many letters you want to print, 29, count it psi, right? Or you can load the, and remember this is using LDR, so it's not using move. It's loading greeting len into register 2. And that will put 29 in there a different way. And then here we come to the heart of today. Okay. The heart of today. Does it only work if the two labels are right next to each other? Yes. Exactly. Register 7 is a special register. You might be using register 7 to hold variables, and that's fine, actually. Register 7 is preserved through function calls. But register 7 has a special meaning. And that special meaning only comes up when you do this command right here. SWI stands for software interrupt. Remember how we were talking earlier in the day that there's the signal command and it sends an interrupt and things like that? This is how you signal the kernel. The kernel, the operating system, the only interface you have between your program and the operating system is this command right here. Software interrupt 0. You might be like, shouldn't I use software interrupt 1 or 2 sometimes? Nope. It's always software interrupt 0. Okay? that means invoke the operating system. SWI0 means invoke the operating system. Every time you do a system call, every time you do a read, every time you do a write, every time you do an open, every time you do a close, and the 100 other, 200 other system calls as well, they are all SWI0. Okay? So how does it know which system call to call? Well, it checks R7. I don't know why R7. I don't know why R7 was picked, but it was picked. So R7 holds a number, and that number is what system call gets called. And in this case, write is system call 4. I have a link on Canvas, Syscall cheat sheet. I have a link to a list of all the different system calls on Canvas. Let's see if these are Unix commands. No, or more high level than that. System call cheat sheet. And so write and open, there we go. So here is the cheat sheet for Linux system calls. So if you wanted to quit your program, how would I do it? Right, I would like for you guys in Discord right now to type it but not hit enter. Type it but don't hit enter. And I want you to write 2 lines of assembly that will terminate your code. 2 lines of assembly. Don't hit return. Just type it. Just type it in. Type it in the Discord chat channel. And I'll leave this open as a reference. So this chooses whatever number you put into register 7, chooses which system call to do, and then SWI invokes the kernel. And when the kernel gets invoked, it checks whatever's in register 7. If you put a 4 into register 7, it will call write. If you put a 6 into register 7, it will call close. If you put a 37 into the register 7, it'll do kill. So I'd like for you guys to type into chat, don't hit return, and write 2 lines of assembly code that will terminate your program. I'll give you guys a second on this and I'll answer questions. Will these syscalls be different for each OS? Yes. They will. But Linux, as far as I know, it's the same on Linux if you are running on x86 and ARM32. I believe the numbers of the system calls are either identical or pretty close to identical across different hardware platforms. I don't think there's any guarantee of it, but it also doesn't matter because you're going to be writing in a completely different assembly language anyway, right? If you're writing x86 assembly, it's going to be completely different than ARM32. But the good news is, because most of the documentation is for x86, it's actually nice that they use the same numbers on ours. But there's no guarantee the numbers are going to be the same. Okay. I got to go to work. I'll DM you my answer, Kearney. Sure. Okay, everybody hit return, please. Move 1 into register 7 and software interrupt 0. Very, very good, you guys. Yeah. And so that will, so if I did this, if I change that to a 1, this will call exit. Okay. So here, this is going to call write. And if we click on write, it looks like we should be able to click on write, but whatever, you saw the man page before. Write takes in 3 parameters, right? It takes write. Write takes in 3 parameters, right? Oh, that's why it was pointing me. Okay. All right. So man to write. So write takes in 3 parameters. It takes in a file descriptor. The file descriptor is going to be in register 0 right there. Register 0 holds 1, which is standard output. And then it holds the address of a pointer. It holds a memory address, which is the string that we're going to print. Please enter your age. And then the third parameter that it takes is the size. And so it's going to write 29 bytes to the screen. and then we invoke write. And then when you invoke the operating system reads the parameters out of R0, R1, R2, and R3 as per normal, and will do whatever it is you ask to do, provided that you have permissions on it. Okay? And so I should probably actually check the return value of write to make sure that yeah, in my code I should actually check to see if there's an error, because it's possible I did something wrong when setting it up. I don't use open almost ever. So I can check for these different errors on it. But yeah, so that's the basic idea. So write will allow you to write to a file descriptor. File descriptor is an integer. So if you open a network socket, you will get a file descriptor, an int. If you want to write to the file descriptor, use the write system call. If you want to read from a socket, you can use the read system call. And you just, if you want to read from a network socket, you just pass in a number. You know, my network socket's 12, whatever number you got before, and then you pass it a pointer to a chunk of memory, and you pass in how big that chunk of memory is. And then, like, if you've got 100 bytes to read from the Ethernet card, then it will read 100 bytes into that array, assuming your array is 100 bytes or bigger. If it's not, then it reads up to the maximum specified by count. And so by using read, write, open, and close, you can basically do reading, writing, you know, opening files, closing files, things like that. I just need to figure out the permissions on the thing and figure out why it's not actually writing into it. And yeah, so that is our learning point for today. System calls. So this is how you actually do things. Because in C, you know, you're going to use printf, but printf is just a wrapper around write. When you do cn is just a wrapper around read. When you do ifstream, that's create, opening a file, right? So all these commands, you know, are just wrappers around these things, because as you've seen, they can be a little dicey to use, right? They're not really user friendly. Maybe I should. Interesting. Maybe I should do that. I don't know. So I'll play with that, and I'll post the actual code to write, you know, ABC to a file in a second. But there's a bunch of system calls, and we'll play more with those in the future. But this is kind of the essentials, right? Reading and writing files, opening and closing files, killing a program, fork makes a new program, and waits for a child process to end. Okay. So that is it for today, guys. I will give you another quiz on the row major ordering, and probably something on system calls. Okay, as the quiz for today. Please enjoy your long weekend. I believe we don't have school on Friday or Monday, which will not affect this class, but if you have classes on Monday and Friday, it should give you a couple extra days off. Okay. So thanks, you guys. Those wrappers are constantly writing to R7. They are, yeah. And so one of the reasons why I avoid using R7 is just because I like to use that open in case I'm doing any system calls. But you can just use R7. It's fine. It's preserved through function invocations and things like that. So there's no reason not to use R7 if you're not using system calls. You have a quick question. All right. I will answer your quick question, but I will see the rest of you guys later. What is your quick question, Mr. Hazard? What happens if you do LDR R1 greetings with no equal sign? I don't know if that'll work, actually. So you just want to use greeting without the equal sign. Nope. Doesn't work. That's the answer. Won't compile. Yeah. So equals is basically used to grab the address of a label, right? And so you can't, yeah. But if you passed in a register there, it would work. You can load from the memory address pointed to by a register. You can use a constant. There's different things you can use with LDR. But for this, if you have a pointer to something within the assembly code, use equals. A lot of the times, though, you're just going to be passed a pointer by C. You know, C is going to have some string you want to print in assembly, and it'll pass that pointer in. But if you have the string If you have the string yourself, right here, then you use the equal sign to grab it. Good question. Okay, any other questions, you guys? Nope. All right. I will see you guys on Tuesday.